Okay, let's look at some practical tips for diagnosing the learning rate. And we'll talk about two. One is monitoring the progress of convergence, and the other is feature scaling. So we'll do those two one by one. If it will let me change. There we go. So diagnosing the learning rate. The learning rate is specific to each problem. It can be too small, it can be too large. Right? And you can tell by plotting the progress of the objective function as a function of iteration. And we'll see that on the next slide. Okay. So if the learning rate is small enough, the cost will reduce in every iteration, and it will converge eventually. But you want to make sure it doesn't converge too slowly. Right? So two things you need to watch out for, as it says here. Keep track of the cost at each update, as I said, at each iteration. Plot a graph of the cost at each update. Okay? Remember what the update is. The update means each time you change the value of theta. Right? So you're going to get a series of values of theta every time you update. Right? The first value of theta you put in here, and you get the second value. Then you put the second value back in the right-hand side and get another one. So that's how iteration works in general. So we can see a schematic of that in the next slide. If it will change for me. There we go. All right, so here you go. Have a plot of the cost function, j of theta, and this is update step. So on this axis, you'd have 1, 2, 3, 4, 5, because you're plotting the cost function as a function of the iteration number, not as a function of theta. Theta is changing, to be sure, but what I'm interested in is the size of the cost function and not the particular dependence of the cost function on the parameters. If you have many parameters, that would be much too complicated. But here, if we just plot the cost function as a function of iteration number, it's a very simple graph. The integers on the x-axis and the cost that you get on the y-axis. So this would actually be a series of discrete points. It would not be a continuous curve. And probably it would be better to represent it that way. But it's all right because, in fact, the tendency is going to be a smooth tendency. And there's actually a mathematical curve that will describe this. I think it's actually quadratic, but I'm not sure. Right now, if you reduce the value of alpha, then you're going to reduce the change in j as a function of update step. So the change is going to be slower, and it may turn out to be too slow. So you can monitor this. Now, if on the other hand, if alpha is too large, it may go like this. And we can see some illustrations of how this happens in just a few slides. All right. So what you do for a strategy is try a range of values. This is actually called grid search. It's a special case of grid search. So you try these values, and notice that the variation is geometric and not linear. So for instance, it's 0.001. I multiply that by 3 to get this. And then here I multiply it roughly by 3 to get this value. And then I multiply by 3, and then I multiply roughly by 3, and so on. So it's a multiplicative series or geometric series. And you want to do that because you're not sure about the magnitude of the learning rate. If you just try 0.1, 0.2, 0.3, 0.4, those are all roughly the same magnitude. And you're going to find that the values the curves don't change very much. So you want to do something like this to pick up the behavior. Then, for instance, if you find the best value is between 0.01 and 0.03, you can home in and be more specific. Right? If 0.01 has a good convergence curve and this has worse, and then 0.03 has a good convergence curve and this one doesn't converge, then you want to home into this interval. So you can refine into successively smaller intervals if you want to. Now we'll move right along to the second tip, which is feature scaling. And this is a nice topic because it has a very geometrical and intuitive explanation. So let's go to the next slide. Will let me? Now, the concept is having features on a similar scale helps gradient descent converge faster. So that's the idea, and this section is going to unpack that idea and give it a geometrical justification. On the other hand, if features are on very different scales, the gradient descent gets slowed down. So what you try to do is you scale features to similar scales. Okay. So for example, if we're looking at the house price example, if we measure house size in square meters, house size can be from 0 to 5,000. The number of bedrooms from 1 to 12, well, 0 to 12 is kind of a robust interval that contains this 1 to 12. And the age can be from 0 to 200 years. Now, obviously, 5,000 is a lot bigger than 12. Now, notice that we could measure the house size in thousands of square meters, and then this would just be 5. And it turns out that that improves the performance of gradient descent. And we'll see that. See, there's no particular reason why we have to use square meters. We could use thousands of square meters or tens of square meters. We can choose the scale, and that will not change the result. If I use the house size in thousands of square meters and I have house size data in square meters, I simply divide by 1,000. So there's no difference in the model using either square meters or thousands of square meters. You can equally use both, and they'll both give the same result. Okay? So suppose you have two features, number of bedrooms and house size. Now, let's suppose theta 1 is house size and theta 2 is the number of bedrooms. So we're going to have a cost function that's a function of these two. Let's suppose we just have these two different variables or features. And what will the cost function look like? So here's a candidate. All right, so what does this say? Now remember, these curves are giving lines of constant cost. So in fact, the best fit is here in the middle, and anywhere along this ellipse, the cost is the same. Okay? Now what does cost mean? Cost means how well the model fits the data. That's what cost means, right? So what is this graph showing me? Well, suppose I start in the middle and I move directly to the right. What I'm doing in my model is I'm increasing the effect of house size on the model. So for instance, instead of saying that the effect of house size on the price is 1.1 times house size, you might say 1.3 times house size. Now that's going to lead to larger estimates for the price if I increase the coefficient of house size. In order to maintain the same accuracy, I'm going to have to reduce the dependence on number of bedrooms. So I can compensate for my overestimation of the effect of house size by underestimating the number of bedrooms. Now notice that if you do this overestimation, underestimation, you can't be at the optimum. At the optimum point, which is a single point here, there is no ellipse, there's just a single point. But if I'm somewhat off, I can wiggle my dependence of theta 2 and theta 1 and still get an estimator that is equally accurate. Sorry, let me get rid of this one on the right. I'm not done yet. See if I can get rid of that. All right, now, it's important, critically important to point out that this is not talking about the correlation of these two variables, bedrooms and house size. It's not true that bedrooms and house size are negatively correlated. If you look at this graph, you'd say, well, okay, house size and bedrooms is negatively correlated. No, it's the coefficients that are negatively correlated. And the coefficients are negatively correlated, in fact, because the variables themselves are positively correlated. If you have a variable, a house with 12 bedrooms, certainly the house size is going to be bigger. So it's kind of paradoxical that the positive correlation of these variables leads to a negative correlation of the level curves of the cost function. Now, is this really accurate of what's going on? One thing that seems kind of strange is that here we have negative values of house size. That's just a mathematical continuation. Don't worry about that. Of course, the optimum is here, so we're not even going to be operating out here where you have negative values. But is this accurate? Now, in fact, because house size goes from 0 to 5,000, a very small change in house size is going to make a very big change in the cost function. All right? And that is reflected in these curves being close together. If you have a contour map and the contours are close together, that indicates you have something steep. All right? And then here, these contours here should be not closer together. So this is not really accurate. Let me do some contortion here to show you more what this cost function would actually look like. Okay, so what I've done is I snipped the cost function and put in another PowerPoint. And I said that house size, a small change in house size, produces a big change in the cost function. So what that means is that it becomes steeper in the house size direction. In fact, the function is going to look something like this. Very much like this. Okay. So I think that's a more accurate picture of what the cost function is going to look like in the case where house size is measured in measured in square meters, and number of rooms is just measured in number of rooms. Now I want to look ahead is that rescaling is basically just stretching this back until it looks fairly circular. Now, you can never make this circular. Feature scaling cannot correct for this correlation between theta 1 and theta 2. It can make it more round, but it cannot get rid of the correlation. For that, there's other methods. The industry standard is called conjugate gradient, but that's beyond the scope of this course. But if you get into machine learning, you can find the conjugate gradient algorithm, and that is actually superior to this to this gradient descent in the case of least squares. The conjugate gradient is particular for least squares problems. Okay? All right, so let's go back to our slideshow, which is here. So as I said, this cost function here is not really accurate. The more accurate picture of the cost function is what I showed. Where did I show it? Is what I showed here. Very elongated and thin. It's actually pretty aligned along the two axes, but it's much longer in one direction than the other. All right. So this here is another possibility, of course, but this would not be applicable in our case. And what this would say is that if I increase the effect of house size, I also need to increase the number of bedrooms in my estimator to get an accurate estimate. But that's not true. Increasing house size is going to lead to overestimates. Increasing the coefficient of house size is going to lead to overestimates. Increasing the coefficient of number of bedrooms is going to lead to overestimates. So in fact, this is the shape of the cost function in this case. Now, what does gradient descent do on a function that has the cost function contour plot looking like this? Well, remember what gradient descent does. Gradient descent is always going to move perpendicular to the level curve because this curve is constant height, so that the direction of steepest descent is perpendicular. So I move perpendicular, I'm over here. And then I go back, 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 and then I go back. So it's wiggling back and forth. So what does this really mean? This function here, in fact, if you look at it in 3 dimensions, it's a long, thin valley. Okay? This valley direction here is the same as this direction here. And the reason that is that because the contour lines are spaced far apart, the altitude is decreasing slowly. Now here the contour lines are close together. The altitude is, well, if you move this way, it's increasing rapidly. If you move this way, it's decreasing rapidly. All right. So what are you doing when you have something like this? Well, you can imagine rolling a marble down the side of this valley, and it's going to go whoop, 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 whoop. Eventually it will go down the gradual slope here, but it's going to take a long time to go around and around and around, right? So that's actually what happens when you use gradient descent on cost functions that are not well, this is called ill-conditioned, right? So you do want to do something to make your cost function look a lot better. So for instance, here you have this, and let's see what it's going to give me. So you have this back and forth. Now what happens is if you see that this is in fact not accurate because you cannot rescale and make it circular. We can show what will happen if you do rescale in a nicer way. But there is no way to rescale to make this circular. So the question is, can I rescale this cost function? Can I stretch the axes x theta 2 and theta 1 to make the convergence better? And in fact, I can't, because if you look at any one ellipse, the extent on theta 2 is roughly equal to the extent on theta 1. So these two variables are occupying the same extent. So you're not going to be able to rescale and improve convergence. Now, if you had a case like this, let me make this taller also. Let's just move it out this way. If you had a case like this would be an extreme case. You could certainly improve this by stretching this out. But you want to stretch it out so that the extent of theta 1 is the same as the extent of theta 2. You cannot correct for the slant. Again, as I said before, you can do that with conjugate gradient, but you cannot do that with simple rescaling. All right, so I reemphasize that this picture on the right is not accurate. You cannot rescale this one to get this one. Now, rescaling does not have to be precise. I don't need to get all of my variables on exactly the same range. But if I have them roughly on the same range, that's going to mean that different variables have approximately the same extent, and that's as good as you can do with feature scaling. Now, you can do the best possible feature scaling and still get very bad convergence. So you can think of an example where that might be. Let me just if I do something like this, something that the theta 1 and theta 2 are almost on a line. So you can think of some example that's exercise for the viewer. All right, so this certainly example is not okay. X4 is from minus 80 to 90. That's more than 10 times the largest range here. And then this is very, very small. So these would not be okay. So you could just multiply divide x4 by 10 or 20, divide x4 by 20, that'd be good. And then multiply x5 by 1,000 or something like that. Looks like you'd have to multiply by 10,000. All right, so that's easy. Now, there are systematic ways to do feature scaling. And so some of these systematic ways have advantages, and they're implemented in Python. So you apply scaling to every feature except x0, because if you think about it, x0 is 1, you kind of want to leave x0 as 1. Now, it turns out that in many cases when you scale, you can simply remove x0 from your list of features. For instance, if you do this, if for every feature you produce a new scaled feature by subtracting the mean, right? So that this mu j is the mean of this feature xj. So that means that this feature has a 0, this rescaled feature has a 0 mean for this feature. So let me just show that. All right, here I have my original data, which is red. So my original values for the feature x1. And you can see these points. If I take the mean, it's kind of here. Okay. So if I take all of these points and subtract the mean, then that simply amounts to taking all this red stuff and shifting it over to center it on 0. Right? So the rescaled variables have mean 0. Now there's a mathematical result that the regression fit for a set of points always passes through the point that consists of all the means of the data. And let me show you that through a picture. So here's an example where I have percent bachelor's degree, and I have per capita income, and I have scatter points here, and I have my linear regression fit. And you can see that this horizontal line is showing me the average of the per capita income coordinates. If I project all these values onto the per capita income and take the average, it's going to be about here at 2.5. On the other hand, the percent bachelor's degree, if I project all these values onto the x-axis and take the average, I'm going to be here. So the upshot is that if you do this rescaling by subtracting the mean from every feature, you don't need the x0 feature. Now you can keep it in there and it won't hurt anything. It's actually a good check. You should get theta 0 equals 0 because the fit should go through the point 0, 0. If it goes through this point 0, 0, you can work it out that theta 0 has to be 0. Now, subtracting the mean does not help with the extent. Right? If I have houses that have square footage from 0 to 5,000 and the mean is 2,000, then my range is still going to be from minus 2,000 to 3,000. And that's going to be a lot bigger than my range of rows. So to make the different features have the same extent, you can either divide by the difference between max and min. In this case, the different features will have exactly the same extent. Or you can divide by the standard deviation. Now, this is actually called a z-transform, which you may have seen in other classes, in probability class, for instance. So that is a standard way of transforming, is to use the z-transform, subtract the mean, and divide by the standard deviation. So which one is better? Well, there's no hard and fast rule, and probably it doesn't matter most of the time. Now, in this case, the range of xj is between minus 0.5 and 0.5. Well, that's more true for the first than the second. If you know about dividing by standard deviation, then there's a lot of tails beyond the standard deviation that is not included in the range. Let me show you what I mean. Now, here are two different features, and this is a histogram of the original feature, which I could call x1, and this histogram of the original feature x2. When you standardize, the histogram will look something like this. Now, you can see that the range is not between minus 1 and 1. It's pretty much contained within minus 4 and 4. And most of it is within minus 2 and 2. But it's not contained within minus 1 and 1. So the max-min feature scaling compresses this more than the z-transform scaling. If you did the max-min scaling, then this point would be minus 1, this point would be plus 1, and this whole curve would be quite compressed between minus 1 and 1. So which one you use depends on situation and preference. Statisticians will tend to use the second one, the z-score, because that's a classical transform. But people who do deep learning who want to restrict their inputs to a certain range and don't want it to go beyond that certain range, they may want to do the max-min scaling. All right. Now, here's an example. Now, which scaling it is, I leave it to you to figure out whether this is the max-min scaling or the z-score scaling. I believe it's the max-min scaling, but you can verify that. You can use the formula. That's a good exercise. Now, in fact, these functions are contained in Python in this sklearn module. And I believe both transforms are there. Now, we have to see what standard scalar is. So here I looked up the documentation for standard scalar, and you can see that it subtracts the mean and divides by s, and s is the standard deviation. So it's using the second one. Now, that's with std equals false. Oh, no, I see. No, with std equals false, you don't divide by anything. So this standard scalar does not do the max-min scaling. So you can do a Google search and see if scikit-learn gives you the max-min scaling that is also sometimes used. And I think that's it. Yes, I think that's it. All right, thanks for watching.